Hello, my name is Daniel Barsky. I'm here with Augury, presenting how Augury works to develop a world where people can always rely on the machines that matter to them, leveraging high-dimensional sensor data in the industrial IoT and using those sensor readings to convert them using machine learning and deep learning into insights for our customers. In my presentation, I'm going to talk a little bit about what the challenge was for us in terms of the data storage and representation, both in the streaming inference setting and in offline batch analytics, training machine learning and deep learning models. I'm going to talk a little bit about how we built a solution and how we powered it with Scylla, how it's really hitting all the marks for us. And finally, I'm going to briefly talk about the next generation architecture and what the future holds in terms of the data streaming pipelines and Scylla combined. Thank you very much.
So I'm a senior data scientist at Augury. I've been with Augury for coming up on 5 years. I have a master's in machine learning. My background before that is in electrical engineering, signal processing, computer architectures. I'm passionate about building simple solutions using complex tools. I love the interplay of hardware and software solutions that incorporate both hardware and software, which is why Augury was such a natural fit for me. I'm going to talk a little bit about what is Augury, what we do, and how we do that. So here is the R&D team circa about a year ago. We've grown a little bit since then. The company was founded in 2011. We're based in Haifa, Israel, and in New York City, in Manhattan, around 100 people. So before I go into what we do and how we do, I want a quick show of hands. How many people here own a refrigerator or have one in your home? I'm guessing pretty much everybody, right? How many of you have had your refrigerator fail? Break down. So those that have your hands raised know how much of a hassle it can be, right? You have to call a technician, you have to wait for them to arrive. You might need to wait for parts, or you might need to wait for the job to be done. In the meantime, you can't really use your fridge, right? Everything in there you have to throw out. You no longer have an excuse for not cleaning it out like you was promised you would do for the last couple of years. You have to make friends with the neighbor that you hate so you can use their fridge for a couple of days. So basically, a critical machine, a machine that's critical to you breaking down, is a massive issue, a massive hassle that we are trying to help everybody around us avoid. So Augury's vision is a world where people can always rely on the machines that matter to them. And we try to achieve that by giving our customers and everybody who uses the Augury platform actionable insights and informative insights about the health and condition of their machines and what they need to do to maintain them, to keep them running longer and smoother. So in the image behind me, what you can see is an Augury installation at a utility plant. I think it's a water treatment plant. So you see the Augury sensors mounted on the pumps. These are a row of pumps. Our sensors basically sample data continuously every hour, every few minutes, or based on an event. Upload that data to the cloud via the gateway that's mounted on the wall. All of the data streams into our cloud, where we apply additional processing, signal processing, time series algorithms, machine learning, and convert those to actionable insights. This machine is running smoothly. This machine needs a bearing replacement. This machine only needs lubrication. This machine can run for 2 years without breaking down. This machine has to be stopped immediately. Our installations are pretty much worldwide, with a massive focus on the United States and Canada. We have some installations in Europe and Israel. We have in the thousands of monitored machines, constantly sending data, constantly uploading new recordings, new samples that need to be processed. And we want to be able to give our customers the insights that they need as quickly as possible with a low latency, without any backup due to massive surges or batches of data uploaded at the same time. So in terms of the solution, this is along the lines of what we've already talked about, right? First of all, when we're onboarding a new client, we connect their machines. We mount our own sensors onto their machines, obviously choosing the right tool for the right job. Those sensors are then constantly uploading data, constantly taking recordings of the machine, uploading them to our cloud where most of our brains are, most of our processing is. We convert those to insights for the specific machine, how good it's running or how bad it's running, what actions need to be taken. And finally, our customers are able to get those insights either via the web platform or mobile app or via email notification, text message, push notification, any way that they want to get their notifications, their alerts. So Augury works in the industrial space mostly. Typical installation would be a production line, a bottling facility, a diaper production line, consumer packaged goods, food production, etc. Basically, we want to help our customers maximize their throughput. So that means less unplanned downtime, less machines breaking down unexpectedly. Also, optimization of their operational parameters, right? Being able to set up the line so that you get the most product per work unit or per time unit. So a few words about the talk that I'm going to present. So I'm going to show a little bit about what the challenge is from our perspective, why we were looking for a solution like Scylla, why we were looking for a solution to store and serve time series data, what our specific use cases are in the context of Augury. I'm going to outline our solution, how we designed our architecture, how we designed the cluster, the data model. And finally, I'm going to touch on two final points. One is an additional benefit that was not the main objective of our original design, but pretty early on, we realized that it's a benefit that we could use out of the box, and that's real-time web dashboards. And the final topic I'm going to cover is the next generation of our processing architecture. So as a quick teaser, we're migrating to a more data pipeline processing oriented architecture from a microservice-based architecture. And I'm going to talk a little bit about how Scylla plays into that migration and into that new architecture. So when we are monitoring machines, like I said, we have sensors mounted on the machine, constantly making recordings, constantly uploading data. We have multidimensional data on the machine, right? We have multiple locations on the same machine. Within a single location, we have multiple sensors. So, for example, we have a triaxial vibration sensor. So, x-axis, y-axis, z-axis. Each one of these sensors produces a stream of data. So, ultimately, when we are reviewing the data in the context of a single machine is very high dimensional, in very high dimension. We are basically looking for both patterns in specific snapshots and trends over time, changes over time, that could indicate for us if there is an issue, first of all, if there is, how severe it is, how quickly it's deteriorating, and how urgent it is to address, right? So on the left side, you can see the typical patterns that we're seeing, at least in some of the parameters that we're tracking, and some of the features that we're tracking. So in some cases, it's a very steep increase. We call it a cliff. That basically means something broke off, something came loose, something changed very rapidly. Alternatively, if it's the other way around, if it's a very sharp drop, it usually indicates that the customer did some maintenance on the machine. Some repair was made. The machine is probably better off. In other cases, it's much more gradual deterioration. That's usually typical with bear-related issues. So if you have a fan and the fan starts to have wear on it, or if you have a bearing that starts to deteriorate, that is a much more gradual process over time that we want to be able to track over a long period of time. And the final phenomenon that we're recognizing are transients, which basically means some set of parameters, some set of operating conditions of that machine triggers a suboptimal mode of operation. The machine is vibrating very wildly, which could overload the machine and cause it to break down unexpectedly. So those are the three major categories of conditions that we're looking for. So when we are talking about the streaming setting, this is basically making a recording at a given time and using that newly received data to update our perception of the condition of the machine, right? If we have a new recording and we think that that recording indicates a deterioration of that machine, we want to be able to process that and convert that to an insight to the customer, convert that to an alert to the customer as quickly as possible with as little backlog, as little latency as we can. So we have a monitored machine. We have several sensors on the machine making recordings based on some trigger, either time-based or event-based. And then they basically take a raw data recording. We can think of those as audio recordings, short audio recordings of the machine, multiple recordings for each sensor, with multiple sensors being on the machine. And that raw data is uploaded to our cloud, and then we do feature extraction. We basically convert that audio recording to a representation that is much more tailored towards tracking the condition of the machine, basically tracking the parameters that we know are indicative of mechanical issues or electrical issues that we're looking for. And that's happening in the cloud. We're basically taking all of these raw data audio recordings, converting them to a few rows, one or more rows in a table. Then we log those rows and index them by both which machine and where on the machine they are, and the timestamp the recording was made, so that when we are trying to understand what the condition of the machine is, we can take a historic view of the last days, weeks, months of that machine's data, and figure out if there's deterioration or an improvement, and if there is, what is the issue, how severe it is, and what we need to do to help our customer resolve that. We have another use case. Basically, what I showed until now is the streaming setting, which is how our customers get their insights. But behind the scenes, what's actually running is we're doing feature extraction, and in a lot of cases, we're running inference for machine learning models, right? So to be able to train those models, to be able to construct the data set, we also have a batch setting, right? Where we look at data from multiple machines at multiple segments in time, right? It's no longer just the most recent data on a single machine and is the context in for processing, but we have to look at multiple events on multiple machines, retrieve those from storage, convert them into a data set that we can later use to train our models. And then we can either do analytics if we want to try to characterize a new feature or a new set of features. We want to try to characterize a new class of machines or a new condition that we're trying to capture. Or if we have enough data and we have the ground truth, we can train a model, deploy that into production, and then we're basically going back to the streaming setting for the relevant machines. So we're looking for, this is late 2017, we were looking for a solution that would help us achieve both of these cases, both the streaming setting, being able to access data in the context of a machine and a window in time, and the batch setting, which would allow us to process the data in parallel fashion to basically automate our machine learning pipelines to make them quick and easy to deploy, make our existing models very quick and easy to retrain. So we basically divided our requirements for such a solution into three categories. So we saw the two settings, right? The streaming setting and the batch setting. So those two have complementary requirements. And we also had, at that point, we were a pretty early stage startup. If right now we're 100 plus people in the company. We were probably around 70 then, maybe 50. We didn't necessarily have the bandwidth to maintain a very complex piece of infrastructure, so we were looking for something that we could roll out and maintain internally in a pretty easy and scalable fashion. So in terms of the streaming flow requirements, we wanted to make sure that we're good on the read rate and the write rate, and also the latency. In terms of the read rate and write rate, we have a few thousand machines monitored, so that's maybe tens of thousands of rows written per hour, so we're not really stressing Scylla or even a lot of its competitors. We're not really in the stress zone. In terms of the read rate, it's probably 2 or 3 orders of magnitude larger, so we wanted to make sure that we're good there. And we wanted to make sure that we're not introducing latency to the processing that's beyond what we're willing to concede. Furthermore, we wanted to have a solution that we could extend easily, that we could add columns, right? If we were adding a new set of features that we're tracking for a specific type of fault, we wanted to make sure that we're able to add those seamlessly without having to do a massive migration of all of our data, that we wouldn't have stuff breaking because we changed the schema, basically. So in terms of streaming flow requirements, those were the main points. In terms of the batch requirements, we also wanted to make sure that we're able to ingest the data in a massively parallel fashion, right? So we wanted to make sure that we were able to access that either by Apache Spark. Right now, we're heavily invested into Apache Beam, which I'm going to cover a little bit later on. It's also a streaming parallel processing system. We wanted to be able to do data migration or even a partial data migration. So if we wanted to run migrations for a set of machines or even for a set of columns over all or some of the machines, we wanted to have a solution that would support that without having to rewrite the entire object, without having to recalculate everything all of the data that we have to process. And finally, we wanted to have safe access to production. So the features that we're extracting, they don't change very often, right? It's a pretty steady representation. And we didn't want to have to recalculate all of the features directly from raw data for every analytics job or for every machine learning model that we wanted to train. We wanted to be able to leverage the data that's being written in the streaming setting without risking either corruption of the production system or overloading of the production infrastructure. Finally, we wanted to have a solution that we, as a small-scale startup at that point, could manage ourselves easily, right? Something that was pretty easy to set up, either in a cloud environment in production, or even in a local environment on a developer's system, or in a test environment, cloud test environment. Something that would be easy to scale up if we saw that we are not hitting the marks on performance, and something that's easy to back up and maintain over time. So we consider a few alternatives. Cassandra was an obvious choice. Basically, there's a very large community there, and that was the first thing that came up when we searched for a columnar database. And the main takeaway that we got from evaluating Cassandra was that it's pretty difficult to deploy and maintain. There's a lot of knobs to tweak, and we didn't necessarily have the resources in the company to venture into that. We also evaluated a couple of other solutions. So Google Bigtable is one that we evaluated. We work with Google Cloud currently, and it's a good solution. It's hosted, it's very convenient, but we were very concerned about being vendor locked, which is why the Amazon solution would be equally risky for us, right? If you're a multinational company, then Google Cloud might not work as well for European customers or for customers in Asia and China, et cetera. So we wanted to be flexible in terms of our deployment options. We also considered time series databases, which were also not really a good fit for us. They're mostly tailored around a single time series, and since our use case is correlating multiple time series to begin with, we thought it would be better to do that at write time than at read time, so that was not really a good fit for us. Plus, they don't usually integrate as well with analytics platforms such as Spark, as well as Cassandra and Scylla and other environments. Finally, Scylla was the ultimate solution that we considered, which we ended up going with. So we were very excited about the fact that it replicates Cassandra's interface in a lot of cases, which means that even if everything went very badly, there's a very clear plan B there. But that was not really the case. We had a bit of a rough experience using RYAC. I'm not sure anybody here has encountered it as a key value database based on the Dynamo architecture. And that was backed by an early stage startup that was really promising early on and then closed and we didn't have any support. So luckily we started evaluating Scylla, we started working with the Scylla team and we got amazing support even as open source customers from Tomer and Glauber and everybody in the field engineering team. So our initial concerns were very much mitigated early on. And that is the solution we ended up going with, obviously, otherwise I wouldn't be here. So in terms of our solution design, a little bit about our data model, right? So I mentioned earlier that the context of a typical query is a single machine, right? It could be all of the data for a machine in a time range, or data from a specific point on the machine. So that was the guiding principle behind our data modeling. In terms of the partition key, we chose the machine ID, right? The unique identifier for the machine, and a quarter. The reason we added a quarter, as I'm sure most of you are doing, is to have bounded size partitions or expectable size partitions. The added benefit there is that we had a coarse-grained way to parse like the time series data on the machine. We could just take the time range query and divide that into the few quarters that we needed, and that gave us a coarse-grained data access. When we're talking about the clustering key, we added the location, the specific location on the machine, such as this sensor is on the motor, this sensor is the x-axis vibration sensor, etc. And we also added the timestamp, so we would have much more fine-grained data access. And finally, all of the features are regular columns in the database. In terms of our cluster deployment, so we're entirely cloud-based. We're using Google Cloud. Since we had the two use cases, we decided on one basically major cluster with 2 data centers. So we have one major key space, which is the production key space, which has a replication of 3 on each of the data centers, right? The production data center is designed for production applications, and research data center is more for analytics and machine learning offline work. So the production key space is replicated in both data centers. We also have another key space, which is the research key space, which is only in the research data center. And that's more of an ephemeral data store. If we want to do any offline analytics, we want to do any intermediate tables, store any intermediate tables based on our analytics workflows. When a production client is running and accessing time series data, it's only doing that via the production data center nodes, and it only has access via authentication to the production key space. When we're running a batch job, when we're running any sort of analytics job, our batch client has read access to both key spaces, to both production and research key spaces, and write access only to the research key space. So that achieves the objectives that I mentioned before, where we're safe from corruption of production data, and we're also mitigating the overload to production infrastructure by not accessing the production data center nodes directly. But we still have read access to data that was written in the streaming setting. So we had our solution for the algorithmic use case, and it was working very nice for us. But we also had another need that was not part of the original design, but early on we realized we could benefit from Scylla as is from it. Basically, we wanted to be able to give our customers introspection into the data, right? If we give an alert, we wanted the customers to be able to go into the dashboard and see on the trend graph where the fault occurred, where the deterioration occurred, right? If we have an explainable model, we wanted to be able to show that on the data for the customer to actually act on our recommendation, right? If you tell the customer your machine is going to break down, some will probably fix it, some will take their time and wait. If you show it on the data, if you show the trend graph deteriorating, they're much more likely to take action, which is what we want as the stakeholders of the health of their machines. So using the same architecture, the same data model, we were able to integrate the web dashboards directly to the data that's written from the algorithm streams, from the algo streams. We're getting really good performance there. So sub-second queries for pretty large batch reads. So if we're loading a year's worth or 2 years worth of data for a machine for multiple features, multiple locations on the machine, the latency added by the query is negligible compared to the actual graphics elements on the web page, which is where we want it to be in this case. Final point about our next generation architecture. So until recently, we've been mostly working in using microservice type architecture in the algorithms and machine learning as well. So that means we have one or more microservices running whatever algorithm we want to run, and they have an asynchronous interface between them. We realize that doesn't necessarily scale as well as the number of machines gets larger as the data rate becomes larger. And also, it's not necessarily an optimal use of our resource pool, right? So we're currently in the process of migration to a streaming pipelines-based architecture. We're using Apache Beam, if anybody's using it. We're on Google Cloud, so Google Dataflow is the tool for the job for us. And basically, the principle there is to decouple the logic from the resource allocation, right? So we have, for example, the ingest pipeline, which basically receives all of the samples from all of the devices in the field, does some enrichment, adds like metadata from the machine, from the customer, groups recordings from the machine, from the same machine at the same time together, and sends it onwards to additional processing. Next up, we have the feature extraction, which basically takes all of these raw data recordings and converts them to relevant features. And then we have anomaly detection, fault detection, all of our machine learning pipelines. And ultimately, those make some API call to generate an alert to the customer when something is detected. So a key element of this architecture is that in between distinct pipelines, you need to have some serialization layer, some protocol that one pipeline would write into and another would ingest. And for us, Scylla was a very good fit for that. Basically, it served as a buffer between the feature extraction, which writes the features, and the elements downstream, which consume them, and helped us decouple and divide the work, divide and conquer, develop that in parallel. We didn't have to do any changes to the data modeling or infrastructure. So quick summary. When we're talking about IoT and when we're talking about machine learning, those two worlds often have requirements that are not necessarily overlapping. And defining the problem correctly, defining the queries, defining the data model correctly really helped us find the solution for us. And that solution for us is Scylla, and it's going strong for Augury.